this particular FDP on the basics of quantum programming. Today's topic is on linear algebra for quantum computation. And the speaker here is Dr. Mustafur Rahman. He is currently a research scientist at IBM Quantum, and has received his PhD from IIT Kharagpur in 2023. His PhD is on the topic of quantum signal processing and optimization. So
Yeah,
we have an expert here who has basically uh, in his initial research area only, taken quantum as a domain.
that's
So I welcome Dr. Rahman. Sir, we can start
yeah.
the
Thank you so much. Yeah, yeah. So this is QT. It should be
three,
QT
sir.
3,
Yeah,
3 years. So okay. And previously, I already made the participants in QT 1 for a industry lecture and QT 02 on quantum information. So welcome you again. And it's really an honor for me to take a few like this opportunity to take few classes on linear algebra. So I'll be taking two classes, one session today for 2 hours, and tomorrow there will be one extended session, 2 to 3 hours. So tomorrow I'll be exploiting some of the things around how this linear algebra is specifically important for quantum computing. So that's why I renamed the paper from numerical techniques in linear algebra to the linear algebra for quantum computation. Okay. So with the book written by Professor Gilbert Strang, Introduction to Linear Algebra, and I recommend this particular book specifically for the UG syllabus. Okay. Now, those who are actually in the postgraduate level and pretty much good understanding of the basic linear algebra, they can start with the book by Horn and Johnson as well as the book by Gallup and Luan. So these two are pretty advanced than this reference one. So those who are pretty much good background in mathematics and wish to understand much from the vector space perspective. So this fourth book is very good for them, like the matrix analysis, and it is an easy integration for mathematics to the engineering subjects, specifically for industrial applications. So written by C.D. Mayer. And a more advanced book is by Professor Saad on numerical methods for large eigenvalue problems. So as many of the quantum computing problem will be solving by the eigenvalue, so it is a good reference book for that. So these are the reference book. And when I start linear algebra, so I always all credits goes to Professor Gilbert Stein. And many of you probably have seen his lecture on YouTube or MIT OCW. Those who haven't, please have a look on YouTube on the lecture series. Okay, lecture series on linear algebra. So why I am referring this course here, because so I'll be roughly taking 4 hours for the linear algebra course, but don't take this subject just for quantum computing. This is a lifetime course, linear algebra, and it has almost, there is no engineering branch where there is no linear algebra. So that's why it is so important for this century, even for your any machine learning, deep learning, AI, whatever, physics, chemistry, everywhere there is matrix. Okay, and this subject is like this lecture series, I mean we all should watch, start from that point. So specifically I'll not cover some of the important aspects, especially on the row space, column space, which are excellent. They are shown in this lecture series, so please have a look in this particular lecture series, suitable for any engineering discipline. Okay, so how many participants are here? Let's check. I hope, yeah, 254. That's great. Okay, so let's start. And I assume very less background on this subject. So I'll start from very basics today. And some important things probably which are not In general, they are not taught in the classroom, but they are important. Those topics I'll be covering. And tomorrow I'll try to cover some of the relation between matrices, graphs, and various engineering branches such as electrical engineering, chemistry, as well as the econometrics, how they are related with the matrices and their properties. So if you see, look at the AICT syllabus, it is written as matrix inverse. So obviously, our special focus will be on that particular topic and the surrounded topics. So let's start with the topic called vectors. Okay, so in our 10 class 10 and 10 plus 2, we have learned that in physics books that vector is something which has length and direction, right? And in general, in plane, like there are some 2D object, right? So typically this kind of line, right? And so this is just there is associated length and there is a direction where it is like placed in the coordinate system. So this is one definition we have learned, and the computer science students they call vectors as ordered list of numbers, list of numbers. So for example, 2 comma 1, 3 comma 0, say -1, -2, 1.5, -0.1, -0.3. So first 1 hour of this class, I'll go very slow just to make the basic part of the subject as simple as possible. Then slowly we'll go for a little complicated thing. So, these are typically list of numbers and they are associated with, say for example, here it's a 2 cross 1 list and the dimensionality is 2. Like the dimension of this list is 2. Here the dimension is 4. Here the dimension is 3. So these all are actually vectors. These are list, and this is the this is the definition given in the computer science literature. Okay. Now the third part is how we define in mathematics. So mathematics defines it in a combined way of both physics and computer science. It tells that vector are some objects, okay, or mathematical topology that follows certain properties. Follows certain properties. And we'll look at all these properties in details later. So what are these properties? So there are two important properties. One is called the vector addition. And the second one is scalar multiplication. Scalar multiplication. Okay. So for example, if two mathematical objects are x and y, then I should be able to do the operation x plus y. And if there is some coefficients alpha, I should be able to multiply this alpha with these objects x or y. Okay, I should be able to perform these two operations, right? And suppose this is my x, so I should be able to do some scaling of x, say 2x, right? So what I am doing, I'm doing scaling, right? Scaling of the vector x. So that's why this particular part is called scalar. That scale a vector, okay? And if there are, say for example, I take, let me take a second color. Say if there is a vector x, there is an object x, say, and another object y, then I should be able to add these two vector x and y. So there are ways how to add these things. So in physics we have learned several theorem like the triangular law, parallelogram law. Similarly, in mathematics we'll formalize all those definitions. So till now, is there any query, or like is it visible my screen and everything to all of you? If you stuck any problem, if you face any problem, please let me know. It's clear. Good. Okay. So now let's define some basics terminology. Although I want to go this session with definitions and all, I'll go little more deeper, but for the time being, okay. So two important thing: span and basis. Okay. So if we have two vectors v and w, these are two vectors, then the span, what this definition tells, I'll explain later visually. Just for the time being, please um, take the definition for now. The span of these two vectors is the set of all their linear linear combinations, uh, alpha v plus some beta w, where all alpha and beta, these are two scalars or some coefficients. So that means alpha and beta, let's take a real scalar. So I'll be using several notations. So let me introduce some notation. So this is the set of real numbers, this is the set of complex numbers, and this is a, say, R n cross 1 is a set of vectors, set of real vectors. Similarly, C n cross 1 is the set of complex vectors. Okay. So when I do not specifically tell what this vector is, real or constant, I define both of them together with a thing called field F, scalar field, because these are scalar numbers that belongs to a field, scalar field F, that can be real or complex. Okay. And I sometimes jointly represent both the set of real vectors as well as the set of complex vector by f n cross 1. Okay. Similarly, for the matrices, I'll be using f m cross n. That can represent the space for m cross n, space for both the real metric space as well as the complex metric space. Okay. So I mean, this is the like just a representation you can represent in a different way. Now, what this means, this particular n. So suppose this is my vector v, and suppose this is my vector w. Now I trace this vector alpha amount. It can be less, it can be more. For the time being, takes it's your alpha v, where alpha is greater than some 1 or some value. Okay. And this is your beta w. Okay. And you are adding them. That means assume they are at somewhere like in this particular plane after doing the addition, right? So this is your alpha v plus beta w. Now you change, you take any value of alpha and beta. So you can see that if you take various values of alpha and beta, both positive, negative fraction, so you will get a like some space. some space where your vectors are actually spanned, right? So that's basically the span. So which is basically set of all their linear combinations of these two vectors v and w, right? So now I'll come to this picture a little later. Now let's understand linear transformation. So suppose there is a vector v, and you reach somewhere here. This is another vector, but what you are doing is basically some transformation of the vector v. So where L of v is basically a function, here, a linear function basically, with vector as input. Now, why I am covering all these basic things? Say for example, this is your quantum state psi in the Bloch sphere, okay, and you want to reach in this particular position after a Hamiltonian simulation or some quantum evolution as quantum phi, right? So you are basically doing a linear transformation on psi, which gives you this state phi, right? So I'll do what sort of this transformation means. All details I'll come one by one. So now in this particular, I'm telling is a linear function, and by defining or by calling it a linear function, I say that in this transformation, origin is kept intact. I won't change the origin over the transformation. This is important. That means, suppose I start this with this vector and this is my origin. After transformation, I should not be somewhere here. This should not be the case. The origin should be intact. There will be some rotation or some changes, some linear transformation. Okay. So this should be the case. So now let's go a bit deeper in this case. Suppose let's take a vector 2, 1 and another vector 3, -2. Okay. And with by taking these two vectors, or in general, you can take these as AC and these two component as BT. Okay. So 2, 1 means you have walked 2 unit across this horizontal axis and 1 unit across the vertical axis, right? So that's why this vector is denoted by this list 2, 1, right? So these are in physics, normally it is written as 2 I cap plus 1 j cap, but in general, beyond 3 dimensions, it's difficult to represent. That's why list is a very easier way to represent. So we can represent this in a metric fashion, where this 3 - 2 you can represent as the first column, and the second particular vector you can represent as 2, 1. So it's a 2 cross 2 matrix. Or equivalently, for AB, you can write as like as another matrix, say ABCD, where your first column is this one, right? AC, this particular vector, right? So, and BT is this particular vector. So that means each column of a vector basically denotes a vector. Often we hide the term called column vector. So these are column of a matrix. Now, what is happening? So now these can act as a transformation. Like if you have A, B, C, D, and you apply on a vector x and y, this is typically a matrix into vector multiplication. I'll also come the complexity, how the complexity is calculated. Those part I'll come also to give a flavor of the computational aspects for the time being. So what it does is basically this means x times the first column vector AC plus y times the second column vector BD. Okay, so which is equals to your ax plus by, the vector, and cx plus dy. Now let's take an example to appreciate this. So basically you can see it's basically linear composition of your vectors, simply matrix vector multiplication. Say for example we take a matrix 3 1, sorry, 3 1 and 1 2, and we want to multiply with minus 1 2, right? So this is actually minus 1 times the vector 3 1, so stretching of the vector with the scalar minus 1 plus stretching of the vector 1 and 2. Okay, so obviously answer will be minus 1 and 3, but let's try to understand the geometry. So suppose this is our vector 1 2, and this is our vector say 3 1, right? So what we are doing, we're doing minus 1 times stretching, right? That means of 3 1, that means there is a phase change, 180-degree phase change, right? So this point is here, right? And the second vector is just twice of that. So just twice of that is just stretching of this thing, right? Now you can bring this entire vector from here, same thing, or you can simply add them. So either you can use a triangular law for this thing, like this vector and this vector, or you pick up this vector from here to here and you'll be getting this particular resultant vector, right? So this is exactly your minus 1 3. So basically this is just how the linear transformation is done or performed by the matrix. So earlier I was saying you are getting v with a transformation L of v, and you are getting another vector say u, right? And this L is basically is a linear function, a linear transformation, and that we have just shown as A. So A is a matrix. A is a matrix. So a matrix is nothing but just a linear function. Okay. And its input is basically a vector, output is also another vector. Just in this way, we are trying to look at. Now, how long I took? Like 20 minutes. Okay. So now let's understand determinant. Okay. Okay, I will not define what determinant is or anything, like you already all know. But what I'll tell is that now I was stretching a vector, right? Now I will stretch an area. Okay, so now determinant um, of a transformation, that can be a matrix basically, transformation, linear transformation, say. Determinant of a transformation is geometrically signifies the change of area. Okay, change of area. So that change can be either stretching or it can be squeezing space. Okay, and it tells that how much change, how much, what determinant tells us is how much area is scaled. Okay, so let's take an example. Suppose a matrix is say 3, 0, 0, 3. Simply a very easy matrix. And we know that the determinant of A is equals to 9. Oh, sorry, is 9, right? Now, what it is doing actually. So it is basically, if you see, if you take a I cap and J cap, this is small area, right? So this point is your 1, 0 point, right? And this point is 0, 1 point, right? So what you are doing is basically you are actually you are going actually 3 unit this side, and you are going 3 unit this side. So you are actually getting this particular area where this length is 3 and this length is 3, right? So if these two lengths are 3, then 3 into 3 is 9. So it is scaled by 9. So earlier area was 1 times 1. Earlier area was 1 times 1. This particular small area, say it is A1. A1 was 1 square unit. Now this big A, right, A2 equals to 9 times A1, right? So similarly, if you take a matrix A equals to, for example, 3, 5, 0, and 2, right? So here you can see determinant of A equals to determinant of A equals to 6, right? So you can easily check that if this is your A1, right? So one side that you can go 3 unit, another side you can go 2 unit, right? So this is equals to 6. So a better way of understanding this, so this is a direct, so where your this particular basis I have taken unit and I have taken unit, but a better way to understand this is when you basically know another relation, right? Although I'll be covering this topic tomorrow. Say this is your u lambda u star, right? So this is your eigenvalue decompositions of the matrix, right? And we know a relation. The relation is basically determinant of the matrix is basically product of the eigenvalues, right? So this relation. So that means there is an equivalent diagonal representation of the matrix lambda 1 to lambda n, right? And associated, you have associated u matrix, right? U1, U2 dot 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 un, and all these are what? All these are basically your orthonormal basis. Orthonormal basis. That means their norm of each such I equals to 1, right? 1 unit. Now, basically what you are doing, what are all these lambdas? So suppose this is your space in a 2-dimensional case, and suppose this is your U1 and this is your U2. Okay, you have a 2 cross 2 matrix, and you have done a eigenvalue decomposition. So what effectively you have? You have U1 and U2. These two are the eigenvectors, and two eigenvalues are lambda 1, lambda 2, and there is the other thing like U1 and U2, these things. So basically the length of U1 is basically lambda 1, and the length of U2 is actually lambda 2. And these are basically U1 and U2 are vectors. And lambda 1 and lambda 2 are the scalars, or the stretching of the vectors U1 and U2, right? Now see, so this is a ellipse, right? And the formula, what is the formula for the area of the ellipse, right? So you can check that basically if it is a like simple rectangle, right? So it's basically height into this this width, right? Say width is W, height is H. So your area is basically W into H, right? So if you assume that this is approximately, it's a basically approximately equals to your kind of rectangular, or you can take small such rectangles as an approximation. you can see that it is basically lambda 1 times lambda 2. Okay, so that is the determinant. So basically it's an area. So even if you can take the integral to get the much closer the area, I mean exact area, to calculate the exact area of the ellipse, basically, then you will find that basically lambda 1 times lambda 2 is basically signifying the area. So that's basically geometric interpretation of the determinant. And this kind of understanding this geometry is important because sometimes you will try to design some algorithm where you try to explore what is the manifold where your solution lies. And then basically you will try to understand what is the minimum area where my solution lies. Even in the, say for example, you are doing some PCA algorithm. So for example, say you take a covariance matrix R, you find the eigenvalues EVD, right? From the covariance matrix, and then you get lambda 1 to lambda n, and you understand, okay, lambda 1 and lambda 2 contains most of the energy of the system, right? And all these lambda 3 onwards to lambda n, they are negligible. They are not important. Not important. And principal eigen, these two values, lambda 1 and lambda 2, this dominant eigenvalues, dominant eigenvalues, dominant eigenvalues you are considering, and accordingly you are taking U1 and U2, not all other U's, because they may contain only noise, right? This only the energy information. So that's why you are only, I mean, the dimension can be very huge, but after eigenvalue decomposition, you find, okay, across this U1 and across this U2, most of the energy are concentrated. All other U3, U4, U5, and UN, they are actually the total amount of energy, that is lambda 3 till lambda n, this area is small. Okay, so that's why this geometrical interpretation is important. Now we'll slowly go to the linear system and the inversion process. So and before, okay, let me first go that part, and then later I'll come for defining some of the other things like the norm of a matrix. And so let me define the norms first. That will help to connect some of the applications. Okay. So inner product and all, I think I have covered in the last lecture in the QT-02 or um, uh, some other instructor probably covered that part. So inner product I'm not taking. So let's go with some more definitions. Norm. Okay. I'll come to more formal ways of like the matrix inversion and other thing. Like, but before that, let me define some more terms to go that part. Okay, this is one another important thing. So basically, norm is a function. Norm is a function that assigns um, non-negative length. This is important. This is important. Non-negative length to a vector of or a matrix. So I'm writing to a vector. So it's okay to write matrix or vector. That's okay. So basically, if I take that vector as V, so basically it has certain properties. So it has to be greater equals to 0. If it is equals to 0, it is equals to 0 only if and only if V vector equals to 0 vector. Okay, so this 0 and this 0 are different. Okay, this is basically a length scalar. Okay, and this is a vector. This 0 is a vector. Okay, so now that means there are multiple components. Okay, 0 0, many such zeros transfer. Okay, then there is a basically if I multiply alpha with a so basically if it is like this is equals to mod of alpha, that is the scalar part will become mod, and then norm of V. Okay, And there is another property called the triangular inequality property. Triangular inequality property. So which tells that if you have two vectors u plus v, that should be either less or equals to u norm u plus norm v. All other equalities like the Chebyshev's inequality and all those follows from the norms law basically. So today I'll show you some important norms across engineering applications. One is called the um, Euclidean norm, or the let's start with the one norm first. One norm, and another name of this is called the Manhattan norm. This is very common in machine learning literature and many transportation systems specifically. So I'll talk about this. So basically, this norm is denoted as V1, one norm, which is simply the sum of all the individual component Vi and I. So what this means? It basically this name is came from a city, Manhattan city, from basically America, and so the road is something like this. Now, if you want to travel from A to B, so you have to go this way. You have to go this way. You cannot directly just simply jump from here to here. So there the roads blockers are there. So you cannot simply go this way. So normally most of the roads we travel, these are in this way. And your total traveling distance is basically individual sum, right? So that's why this kind of distance is called the one norm distance, okay, or the Manhattan norm distance. And so basically you have individual component wise sum, okay. Second norm is very also common. This is called the Euclidean norm. Euclidean norm, so denoted by V2, where you take the individual squares, right? So Vi square. Okay. So now this is often used in error calculations, right? Mean square error, MSE, right? And many other places, Euclidean norm. So basically, if you are in a coordinate system, you are at a point A, and in the Cartesian coordinate system, you just want to calculate the distance between the two vectors A and B. So if its component are x1, x2, and its component are say y1, y2, you simply take the Euclidean norm in. So basically root under x1 minus y1 square plus x2 minus y2 square, right? So that's basically your Euclidean norm. And similarly, you can define P norm. So basically in quantum literature, you will see various norms such as diamond norm, okay? So basically Euclidean norm is specifically this is related to quantum fidelity calculation. And we have seen this in quantum swap test circuit. Okay, where you have two quantum state phi and psi, and you are interested to compute this inner product square. Okay, so this is basically a two norm, Euclidean norm of two quantum state phi and psi. Similarly, you have diamond norm and other several p Saturn norm. So diamond norm is one type of one norm that is exhaustively used in the quantum literature. So p norm is defined as so sum over I um, whole to the power p and whole to the power 1 by p after doing the summation. For matrices, there are some additional norm. One is called the Frobenius norm. Frobenius norm. So it's typically written as AF. Um, So this is square root of sum over row and column ij aij square. So individual element square and then square root. And there is a norm called the infinity norm. Infinity norm. So infinity norm for a vector is denoted like v norm infinity, which is the maximum element present in the vector, max over I vi, and modulus of that. For a matrix, say a matrix is denoted by A, the infinity norm for the matrix is defined a bit differently. This is max over I, if I is your say row, okay? Then sum over j is your column, right? Aij, right? So basically, so maximum, basically sometimes we say maximum column sum, okay? So this is basically, so sorry, this is called the maximum absolute row sum, okay? Maximum absolute row sum, okay? Now, there is another norm called the trace norm or the nuclear norm. And now you can ask me why I am just covering all this. Out of these different norms, is it possible to classify or group them from quantum calculations? Yes, yes. So two norm is very frequent when you try to calculate. Tomorrow we'll see. So basically, the distance between various quantum states. One norm is very common, like the diamond norm I told for specifically in quantum information, and some of the other norms why I'm referring this because in certain algorithms you will try to find the sparsity based the complexity advantage for certain sparsity. So there this kind of various norms where which is suitable for what, right? So I'll cover that part. Yeah. So trace norm or the nuclear norm is another name is called the trace norm. Yeah. Trace norm is basically also written as A star, which is basically sum over all the singular values of the matrix. Okay. So they are some sort of distance, all these kind of norms, but they used in various specific context. So where the sigma I are the singular values of this matrix A. Now, what is singular values and all? Tomorrow I'll cover extensively on the decomposition methods, starting with QR, QR, EVD, all different various decomposition methods. So basically, which norm shall we choose? Okay. So if you see the unit ball representation, so those who are pretty much already used the optimization methods, they all know this kind of methods, but for now. So as p is less, okay, if you take less and less p, the solution will be sparser. More and more sparse solution you'll be getting. Okay. So for example, if you take p equals to half, so although most of the books defined p starting with 1, right? So this is the geometry for, okay, I haven't drawn it properly. So this is p equals to half. Then if p equals to 1, you can see the arrow. So a bit more smooth for p equals to 1. P equals to Euclidean norm. So basically it's a circle shape equals to 2. And then p equals to infinity is basically square shape. Perfect square shape. So these are various geometries for the norms. Okay. So this is also known as the super ellipse. Okay. So now let us in our product Diamond norm is basically a special type of one norm suitable for the analysis of quantum channel or the Krauss operator based quantum communication method. So that is this one. This norm is often used in quantum communication. Okay. Um, and I'll come what are the various relations with the quantum formalism tomorrow again. Okay. So now let's come to the point, these inversion methods. So let's start with the linear system. So, I mean, most of the engineering applications or many engineering applications, we are often represent the input-output relation as this. So there are some unknowns, and their relation is something like this: A11 x1, A12 x2, so on up to A1n xn equals to B1. Similarly, a m1 x1 plus a m2 x2 plus a mn xz equals to bm. So if you look at these equations, like even if I take one more, say a21 x1 plus a22 x2, and this is a2n xn equals to b2, right? So you can see that there are so certain variables x1, x2, and up to xn, which is related to a system output b1, right? But what combination of the inputs gives rise to b1, we have to compute those actually combinations. But from one equation, it is difficult to solve this, right? So we have several such realizations. So here, these combinations like a21 x1, then a22 x2, a2m xn, so on up to how many such equations are possible. So you can see how many unknowns are there. So if you just break this equation in this way, it is easier to look at, say, a11, a1n, and a n1, and a so mn, right? Mn, right? And I can write the x part here, x1, x2 to xn, that gives the b1, b2 to up to bm. So basically, you see that if you multiply the first row versus this column, you get this first equation. Similarly, if you multiply the last row with this particular column, you get the last particular equation that is satisfying this particular matrix times the vector is equals to another vector. So this is simply linear transformations, right? And here you can denote this as a matrix A m cross n, which is a linear operator acting on this particular unknown variables, right? So how many unknown variables are there? There are n number of unknown variables. And how many equations are there? There are m number of equations. So m equations and n unknowns. And we basically try to solve this equation to find all the unknowns given the m equation. So this is objective of many applications. So tomorrow we'll see some of the electrical engineering and chemistry applications where we are interested to find some of the solutions, right? So so this is a m cross n, and this is your x unknown, and we call it as a vector. So all the variables we club together, right? And we named it as a vector x bar n cross 1. And similarly for the b, we call b bar m cross 1. So what is the dimension for this? It's m cross 1. So b bar is basically, let's take real, or in generic, we can take m cross 1, your x, that is the unknown. We are trying to find the solution for x, which is basically n cross 1. and our A basically some m cross, so this will be small letter, right? M cross n dimension. Now what we have ax bar equals to b bar as our equation, and we are trying to find some estimate on x, like, so which is basically the solution should be something like that, a inverse b, right? If you pre-multiply with a inverse, so x will be a inverse b. But this is not a simple problem. This is not in general always, it may not always, may not be possible, always may not be possible. Okay, so if A is a non-singular matrix, if A is a non-singular matrix, then there exists a unique solution. There exists a unique solution x bar. I always write the solution as x hat, okay, because from estimation theory background, okay, because sometimes A has noise and all, like we have seen in the communication system. So I'll come application part later. So x hat equals to A inverse B. So if and only if A is a non-singular matrix, okay. So then basically we can get the solution x hat equals to A inverse B, and in this particular case, uh, m m has to be equals to n. Okay, first of all, number of rows equals to number of column, so which means that a system with n equations, a system with n equations and n unknowns, even if it is given, we may not get a inverse. That may be the case. So this is one condition, but there are additional requirement. Then the natural question is then uh, when A inverse will exist, like existence of inverse. So when we can get some solution x hat, right? So there are many answers. Like let me write some equivalent statements. Equivalent statements. So first of all, if A inverse exists, you can directly compute A inverse. If A inverse exists, right, that means A is a non-singular matrix. Non-singular matrix, okay. Second is if rank of A equals to n, that is full rank matrix. Third is you start with a matrix A, okay, and you perform the Gauss-Jordan elimination. Gauss-Jordan elimination. Okay, I'm not going to any of these methods. Gaussian elimination. These are very standard, and I'll suggest you to go to the reference books, right? So and especially the lecture series. I'll only cover some important summaries which are important for engineering and specifically to quantum technology applications. So you start with a matrix A and you reach to a matrix identity matrix, right? If you can do that. And fourth point is if Ax bar equals to 0 vector, okay, and this will happen if and only if x vector equals to 0 vector. If this is the situation, all these four statements are equivalent actually. So basically, A has to be a full rank matrix. or there is a direct inversion calculations, or I should be efficiently be able to compute an identity matrix using the Gaussian Jordan method, or there is a n number of independent columns and n number of independent rows. So there are many equivalent statements, but these four are some summary of those equivalent statements. Now, so basically, what we do in the Gauss-Jordan method. So you are given a matrix A and you prepare a augmented matrix AI, right? So basically, for example, let's take something like this: 1, 2, 3, 5, 6, 7, 8, 8, 9, 10. This is your matrix, and you want to find the inverse of this. So first, what you do? First, we do with the augmentation with I, where I is equals to your identity matrix 1, 1, 1, 1, 0, 0, 0, 0, 0, 0, right? So then after doing the transformation, that means all your the row operation, we do several row operations such that uh, here we get an identity matrix and here we get A inverse. Okay. So basically first part will become 1, 1, 1, and here all elements will be the component of A inverse, right? So if you do the Gauss-Jordan method, so how many operations we do? We typically do n to the power 3 multiplication and n to the power 3 minus 2n squared plus n additions or subtraction. So altogether order of n cube is the complexity. Okay. Okay, somebody just using the reduced row equivalent form. Yes, you can do reduced row equivalent form. Correct. So I've so that's why initially I told like to maybe in the next lecture, or even if you some of you are new to linear algebra, please go through Professor Gilbert's lecture series. That will be very much beneficial. And I'm just forwarding some of the important aspects and some advanced part. Now, one thing is called the sensitivity. Okay, what is sensitivity? Suppose you are able to get a solution A inverse. Okay. Now, suppose your application is something like this. You have a transmitter, same communication example that I covered probably in the QT1 or QT2. You transmitted some symbol X. Your receiver does not know. It is receiving some Y, and there is a channel matrix H. Okay. So this is simply Hx equals to Y. Same equation. And you are interested from your received signal Y, you are interested to estimate what was transmitted. That is H inverse Y. This is what you are interested to transmit, right? But in the medium, there might be noise is added to the system, either in the thermal noise or in the environment. Channel does some impairment. Okay. So and suppose your equation is not this. Your equation is H plus W times some X tilde equals to Y, right? And from this equation, you are trying to estimate the transmitted symbol, right? So these are real practical challenges. So that's why there is a term called sensitivity. So what is that? Non-singular matrix, a non-singular matrix A is said to be ill-conditioned. This word is important. Ill-conditioned. Ill-conditioned if a small, if a small relative change, in A can cause a large, small change in A can cause a large relative change in A inverse. in A inverse. Okay, and this is measured by, this sensitivity is measured by with a quantity called condition number. Condition number denoted by K equals to norm A times norm A inverse. Now you can ask me which norm shall I choose? You can take one norm, you can take two norm. Depending on the application side, people prefer which norm they should take. Either it's a communication application, control system application, it's a chemistry application. So they knows which is the better norm for them. So it's some matrix norm. Okay, this is some matrix norm. So typically you can also denote it as like this way also, norm A by um so sorry, norms A times norm A inverse, right? So this is later you will see that this is also equals to, this is I'm not giving the proof, but this is also equals to lambda max by lambda min. Maximum, if there is a eigenvalue decomposition exists for the matrix A, then this is equals to lambda max by lambda min. And typically we say a system is a good system if K is less. Okay, so if K is more and more, then basically any small change in A will highly impact in A inverse. So what is happening? So you are only adding a small noise to the channel H. Okay, then your solution X hat, which contains the A inverse, right? In direct solution, H inverse. Now it will be not only H inverse, there will be additional term, but that term will impact a lot if the condition of the system is poor, right? That's why people keeps more when they design the MIMO system, like multiple antenna input and output system. So how many antenna they should put in the input and how many antenna they should put in the output. So they create a diversity of antennas, right, such that the overall system, okay, the health of the overall system is good. Now you can see if you have a system, any system, a country can be a system. Say our body can be a system, right? So lambda max is the maximum eigenvalue, and lambda mean is the minimum eigenvalue, and that ratio, if it is less, right, then we say our body is in a healthy situations. That means if this variability is very high, right? Say for example, if a country the rich person is very rich and the poor is very poor, right? So that means the condition of the country is not that good. So it is something like that. So similarly for a matrix, lambda max by lambda mean, the difference should be as close as possible such that K is less, and if K is less, then if there is a small tolerance in the system, still you can have a better solution, right? So it is related to a bigger term. Okay, can you explain what is eigenvalue decomposition here? There is a question. Okay, tomorrow I'll totally 3 hours I'll take for EVD, SVD, and all decomposition techniques. Today, please take it just for definitions. Okay, so nothing, no theories. Okay, so now, so suppose my system was A and there is a noise added in the system A plus W, and input is X tilde and the output is B vector. Okay, so relative change in the solution is relative change in the solution. Suppose X should be the solution, but there is a relative change X minus X tilde norm by X with respect to the original, right, which is roughly approximately A inverse times W. Okay, and it is equals to A inverse times A W times. So what I have done, I just so this is basically roughly equals to this. Now I multiply with A and divide with A, right? And this is basically my condition number K times W by A, right? So now you see Now, if my condition number is less, right? So some tolerance if I do in W, still the relative change in the solution will be small, right? If I have some change, but if K is very high, so that means small change in A will impact very high in the solution. So you can compare with the terminology from right hand side and the left hand side. So there is a formula called the Sarman-Morrison formula. Sarman Morrison Woodbury formula. Uh, you don't need to remember this formula. Just understand the context. Now suppose you are able to compute A inverse somehow. But suppose you are given a problem like the problem is A plus B, how to compute A plus B whole inverse. This is the problem. Okay. And this is approximately A inverse minus of A inverse B A inverse. So there is a theorem how to calculate this. The theorem is given by Sarman, Morrison and Woodbury. And the theorem is A plus CD, other two matrices, whole inverse equals to A inverse minus A inverse C. There is a big proof. I am not giving the proof, but just mentioning here so that you can keep a touch of this. So because many times you will be working with engineering system corrupted by noise. So these additional part will be added in from your system. And then probably you are trying to find a solution given the noise corrupting your system. So this kind of formula will be helpful to calculate the solution. Right. So I'm pausing here for 2 minutes, right? And then I'll start, I think most important part is vector space. Vector space and fundamental subspaces. So I don't have any slides, so I'll be writing everything on hand. So yeah. So any questions so far? Previous slides. Okay. Which book should be preferred for detailed numericals on this topic? Okay, for detailed numerical, I'll suggest the if you are so if you ask me for the basic books, it will be Gilbertstein. I mean, there is a lot of numerical examples and exercise. A bit advanced book will be C.D. Meyer, Carl D. Meyer book. These two books will be sufficient for numericals. Yeah. Today we'll be solving some numerical uh, at 3:30 on it's 2 to 4. Okay. So maybe last 15 minutes we can try to solve some numericals. So okay, so let me start. So okay, vector space all of you know, but let me start uh, with a much simpler form or way. So while you talk the vector space, because quantum computing, it's all about you are working on the Hilbert space, and that's basically a vector space, okay, with certain properties. So a vector space involves whenever somebody asks you what is vector space, so it's basically it talks about or it involves two sets, and these sets are V and F and two operations. So these operations are vector addition and scalar multiplication. So all the questions regarding eigenvalues and singular values I'll cover tomorrow. Multiplication. So, and it is defined as follows. So there are only two things, two sets, V and F, and two operations, addition and multiplication. Okay. The set V is called a vector space over the field F, just a set, okay, field F, while it follows certain properties. Okay, there are many properties. I'll be only covering four important properties. Even you can remember only two properties. First property is that x plus y, if these two are vectors, like x and y two vectors, so it will belongs to the set V if x and y individually belongs to V. If there are two elements x and y, they are basically part of the set V. This is a set V, and then basically if I add these two vectors, that should also belongs to the set V. So this particular property is known as uh, closure property for vector addition. Closure property for vector addition. Second is there must exist a vector zero vector such that if you add this zero vector with any vector, you get that particular vector. Okay. For any such x vector belonging to the set V. Okay. And we need to remember another property, that is if there is a scalar x, then alpha time x belongs to the set V for any alpha belongs to the scalar field F. So basically if there is a scalar and there is a vector x which is belonging to the set V, then alpha times this vector also should also belongs to the set V. Okay. So for any x belongs to V. So this particular property is called the closure um, closure property for scalar multiplication. And this you may not remember that this is important. So if there is a constant 1, so 1 time x should be equals to x for all x belongs to V. So this is just a simple corollary. Now, if somebody of you just haven't taken this, just take a screenshot. So just to save time, I'll just go this part bit quickly, but the part which are important to understand, I'll go slow. Okay. So then subspace. So let S be a subset of V. That's all. And it follows all properties of vector space. Then we'll call it as a vector subspace. That's all. So S is a subset of the bigger set V, and it has to obey all the properties of the vector space. So that means if there are two elements x and y, they belongs to the set S, then x plus y should also belongs to S. And if there is some alpha belongs to the scalar field F and x belongs to S, then alpha times x should also belongs to the set S. That's all. Okay. Um, yeah, there are other, so there is a question, what is about the inverses? Yeah, there are about 10 to 12 properties. I skipped many, like I'll provide you the notes, handwritten notes, so everything is written there. Just to save time, I am only uh, pointing the most important properties. Then the third part is the spanning set. And now why I just defined subspace. Okay, there are four fundamental subspaces. I'll come just after the spanning set. Four fundamental subspaces called the column space of the matrix A, the row space of the matrix A, null space of the matrix A, and the left null space of the matrix A. So this important for subspaces, specifically when you try to design inverse of a system. I'll come. Now, spanning set. Suppose there is a set S and the element of the set V1, V2 to up to Vr, right? Now the subspace which is spanned by S is basically you take the linear uh, linear combination of the vector alpha 1 V1 plus alpha 2 V2 plus so on up to alpha r Vr. Okay, so this particular linear combination of vectors is called the space spanned by S. So now let's take an example. Say for example, if we have the unit vectors E1 equals to 1 0 0, E2 equals to 0 1 0, then E3 equals to 0 0 1, right? So what are the things we have taken? Just so in a three-dimensional point, so just 1 point, second point, and third point. So basically 1 0 0, this is your E1, this is your E3, and this is your E2, right? So then basically it creates a space, right? If you take the linear combination of all these three, like alpha E1 plus alpha 2 E2 plus alpha 3 E3, then you can cover the entire R3, right? So that's why it span the set E1, E2, and E3. They span the entire R3, right? So this is the spanning set, and now most important part we'll be covering, that is the four fundamental subspaces. If any of you haven't taken the notes, you can take it from here. Four fundamental subspaces. Now this part I'll go very slow. This is important. Okay. So let f is a linear function. Let f is a linear function that maps Rn into Rm. Okay. And R of f denotes range of f. So every function there is a domain and range, right? So we take a function f, which is a linear function, and the purpose of this function is to map like Rn to Rm. and there is a range associated that is called R of F, right? So, so mathematically we can write it as, okay, Abhijit C, please. Shouldn't S include the origin S? Of course. So anywhere, like, okay, previous slide might be this one. So I put dot dot dot. So 0 is always a component of the vector space, okay, by default. Otherwise, the properties will not be satisfied. Okay. So RF denotes the range of F. So now mathematically you can write R of F is the set Fx where X is belongs to Rn. Okay. So if I have some X is basically some vector, right? Say for example, Ax equals to B equation, right? So what is my X? X is basically Rn cross 1 vector and B is basically Rm cross n 1 vector, and A is basically R m cross n, right? M cross n, n cross 1, m cross 1, right? So here X is n cross 1. Now A is acting as a function here, right? Function on the vector X, which is producing B. So RF is the range, which is the vector B here, output, right? And it is a subset of Rm now, right? So it is the set of, of all images as X varies freely over Rn. So if X varies freely over Rn, then R of F will vary over Rm. Okay. So this is the condition. Let's take assume all these things. Then what we say? The range of every linear function, every linear function f Rn to Rm is a subspace of Rm, and every subspace of Rm is the range of some linear function. So I'll make these things more and more clearer with much more visual thing. So forget this definition. Okay, let's go ahead. So with example and geometry, we'll try to understand. Suppose, sorry, just 1 minute. Suppose V1, V2, Vn is a spanning set for V. Okay, so that means you can write it as sum over alpha I Vi for all I, such that alpha I is some scalar. Okay, in this way, and we can stack all the vectors Vi as V1, V2, v3 dot vn. These all we can stack them, right, and call as a matrix m cross n, and we can stack all the alpha, okay, and denote by the vector x alpha 1 alpha 2 dot alpha n transpose. Okay, transpose means a column vector. Okay, so then we can write alpha 1 v1 plus alpha 2 v2 so on up to alpha n vn at stacked such v1 v2 up to vn times alpha 1 alpha 2 dot alpha n, so which is actually equals to a x bar, right? So this part is a, this part is x, so basically a x bar. So that means f of x equals to a x bar is a linear function. Is a linear function, and 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 here a generates the subspace of Rm. Here a, this is the function which generates a subspace, of Rn, sorry, Rm. And similarly, if we have A transpose, right, A transpose can generate the subspace for Rn. So how I'll come to this part, how it is generating. Does this mean the space is n minus 1 dimension? Not necessarily. Now go specific. So column space and null space and row space. Step by step. Um, so R of A, this is called the space spanned by the columns of A. So that's why it's called the column space, or also written as C of A. Okay. So basically, if you see the matrix A, so A11 up to A1n and AN1 to up to ANN, and if you first think this is called as a first vector V1, the second is as V2. So you take each and every column V3 up to Vn, such column. This one is Vn, right? Right. So with this, all these column vectors you take, and you take the linear combination of all these column vectors, you get a space, right? And that particular space is called the column space. Okay. Now similarly, you take R of A transpose. Now if you take the transpose of this matrix, right? So this will become the column of, so basically this is A. Now if you do the A transpose, right? So basically your matrix will be now A11, and this will be A1n, right? Sorry. How we So this will be now A1n, and this will be your AN1, and this will be your NN. So you can take instead of n cross n, you can better take, say, I'll call it as a m cross n matrix. Then that time it will be mn, okay, and it will be your mn, okay. Just so now basically earlier it was my column, right? So now A transpose, this is my column, right? So that means this particular thing is coming here, right? In this way, right? So that is the R of A transpose, right? So that is the space spanned by the the rows of spanned by the rows of A or columns of A transpose, you can say, or column of A transpose. Okay, column of A transpose is called the row space. Okay, so how to write these things? So like if B vector belongs to column space of A, that means B equals to AX for some X, and if A belongs to row space of A, it means A transpose equals to Y transpose A. Now vector comes in the front and matrix come in the this part, right? So that means earlier our structure was this way, AX was this way, and we are getting this equation, right? So this was our A, this was our X, and this was our B. Now this equation changed. So this equation is now, this is your A, this is your A equals to Y transpose, means this one, Y transpose times the matrix A. Okay. So structurally the thing is changed. So earlier the structure was like this way, X equals to B. Now this is the column space picture. Now the picture is like this. Okay. So this A transpose equals to Y transpose A. So why I am just converting in all these pictures? So because always my system might not be square, always my system might not be full column rank or full row rank. So whatever be the problem statement, like the number of unknowns may be more than the equations, less than the equations, or equal to the equations. So accordingly we have to look where my maximum number of rows or columns lies, and accordingly I have to find a solution for the system, right? So I'll come to the solution part. I have some time. So let's define the null space. So null space is basically, null space of the matrix A is basically is the set X, okay, for which you have a X bar is the zero vector. So you get a basically for all values of X, such X for which X equals to 0, not B. Okay, zero vector you reach, and that is a subset of Rn. Okay, so because you are taking the X, and X always is in the n dimensional space. Okay, and B or Y, that is AX bar, that is always in the m dimensional space. Okay, so this is together in the m dimensional space. This is in the n dimensional space. Okay. Now there is something called a normal equation. So we may not always get the solution for AX equals to B, right? So because A might not be square, and there might be this system may not be always homogeneous equation. So that's why we take A transpose A X equals to A transpose B. We pre-multiply with A transpose, and which basically if A is your M cross N matrix, then A transpose A will be equals to your N transpose N matrix. Now it's a homogeneous system, and that's why this particular equation is called the normal equation. And we will try to design solution from the normal equation for non-homogeneous system. Okay, so this is a normal equation. So this is all are the prerequisites for linear algebra, what I just covered in roughly 1.5 hours. Now we'll try to go for some solution. Okay, solution is very standard. Solution, you just write some code in some Python or somewhere, you will get the solution. But what we need to understand is how to find solution or how to design solution. That is important, for which all these prerequisites are important. So now let's calculate inverse. Today we'll be learning various types of inverses. For example, left inverse, right inverse, pseudo inverse. Because in school normally we learn the direct inverse. So that is not helping us much in the real applications. But these are the things where we have to find some solution. So now let me draw a picture. So okay, so this particular part is called the row space. This part is called the null space. This part is called the column space. This part is called the left null space. So this part is a n-dimensional space. Okay, I'll come. The fourth one is the left. Okay. So basically, I defined the null of A transpose equals to the set X for which X bar equals to 0. Similarly, null space of A transpose is the set Y such that Y transpose A equals to 0. Right? And why I say Y or B, I sometimes I say B, or sometimes I also term them as Y. Okay, so they are same thing. So basically you see whenever it is B, it's a M cross 1 vector, right? So basically it's a M dimensional thing. And the solution you are getting like Y transpose is basically an N dimensional thing. So it's basically a subset of, so subset of Rm. Okay, so that's the fourth basically fundamental subspace. I missed that. Okay, thank you for reminding. Okay, so now suppose we take a vector x here. Okay, and my equation is saying ax equals to say b. Okay, or y, whatever it is. So basically ax always lies here because ax is m dimensional and x is basically n dimensional thing. So this part is Rm and this part is Rn, right? So I have to get, so basically this particular vector, right? So Ax bar, right? So basically if a rank of a matrix is R, then the dimension of the row space is R, dimension of the null space is n minus R, because R plus n minus R is n. So altogether it is n dimensional space, and the dimension of the column space is M, and the dimension of the left null space, that is basically transpose, this is n of A, this is basically your M minus R, right? So altogether it will be, rank will be R. So R plus M minus R is actually M dimensional space. Okay, so now there are, so this is basically I had one picture. Let me go to that picture and I'll come back here. Yeah, this one. So this is so you are staying in a n dimensional space. Your function is transferring you from n to m with an application of a linear function, that's a matrix A. So basically your initial vector now, so your x vector may have two components. One is the rxr component and one is the null space component. Means your solution may not be an exact solution because it may be a rank deficient system. Okay, so if it is a rank deficient system, so basically Ax equals to b is from here to here, but x may have two component, r component and x component. So this is your n component and this is your r component, right? And if you add these two vector, you get this particular vector. Okay. So this particular vector, you are projecting it to the column space, right? And to get your solution. So that's basically B. So it has two component, Ax r equals to B, Ax n equals to 0, because null space, by null space definition, x equals to 0, right? And for which component you get the 0? For only x n component you get the 0 value, right? So because x has two component, xr and xn. So now basically to get the solution, right? So we have to project it from project it to the column space, right? But why do I need to project it to the column space? So let's come to that picture first. Then again I maybe come here, maybe coming here. Yeah. Yeah, I was here. So there are various things. First is called the two-sided inverse. It may be the case that A inverse equals to identity equals to A inverse A. If we are very lucky, in that case, A inverse equals to identity, that equals to A inverse A. This will only happen if rank equals to M equals to N. A square matrix with full rank. Square matrix with full rank. Okay. How to solve this? You can easily, by analytical method, you can use Gaussian elimination method, Gauss-Jordan method, or iterative, by iterative, you can use conjugate gradient method or Newton's method. So these are several methods to solve this kind of equation. So this is very standard. Okay, there is no problem. Now, if it is not the case, so then basically there is something called a left inverse. Left inverse. Okay. So the left inverse is basically also known as the full column rank matrix. Full column rank matrix. That means R equals to N. So if R equals to N, that means this does not exist. So basically N minus R equals to 0. So so basically R equals to N, that means N minus R equals to 0. You only left with this space. So only you have the row space. No null space. Okay. So the only null space is the 0 vector in that particular case. Okay. So R equals to N, then N, what is N? N is basically columns, N number of columns which are independent, right? But probably N is less than M. Okay, so M is the number of rows. So there is more rows, right? And less columns, but all the columns are independent columns. In that particular case, we say this matrix is a full column rank matrix. Okay, so the only null space is null space here is the origin. Okay, the origin 0 vector. Okay, so all are independent columns. Then in this particular situation, so we have to target n. Okay, because n equals to r, and that is the full column rank matrix. That's why we will be doing A transpose A, right? A transpose A in this particular case is invertible. So because A transpose is basically what? A transpose equals to your n cross m. A is actually your m cross n. So A transpose A equals to your n cross n. Now it's basically a full rank matrix, n cross n, because M is basically more than n. So you better take a subsystem, right? So you have more rows and less columns. Okay. So you take a better subspace of the system, right? Where after doing the multiplication, right? After doing the A transpose A means multiplication, you find a full rank matrix of that A transpose A part. So then what we do, A transpose A whole inverse A transpose. So it's something like this is not the right way to write, but just to make to understand that it is A inverse A transpose inverse, right? Times A transpose, right? This part cancel out identity. So this is roughly A inverse. So this way I shouldn't cancel, but this is roughly equals to A inverse, right? So this is called the A inverse left, right? And dimensionally it is fine because it is n cross n, right? And this is basically your n cross m. So what you get is basically this A inverse left is with the dimension n cross m, right? You see, rectangular matrix we can never find the inverse, right? So that is defined for the direct inverse is defined only for the square matrix. So that's why what we did, we have computed A transpose A, which is a square matrix, as well as it is full column rank because it is n equals to r, right? It is full column rank. That's why we have computed the inverse of that particular square matrix part, which is invertible, times the A transpose, which gives roughly A inverse of the matrix. Okay, A inverse left. Okay, so then basically to verify that this works, what we do, A inverse, sorry, um, to verify that it works. So basically what we will do, A transpose A whole inverse A transpose, right? So this is my left inverse, A inverse left, and again I multiplied with the matrix A, right? What happening? So what is happening? So basically A transpose A whole inverse A transpose A, take it as a matrix B. So B inverse B, where B is a square matrix. So if I terms A transpose A equals to another matrix B, which is a full column rank matrix basically and square matrix as well. So I am getting B inverse B. So it should be identity, right? So it's identity matrix. That means the matrix multiplication holds. So what was the definition of matrix inversion? Was that if I have Ax equals to b in equation, there exists some matrix A inverse, right? Such that basically you get X equals to A inverse B, right? So that's why we have to find that particular existence things. So in this particular case, we have seen that we have found some A inverse left equation for which if we multiply these things with the matrix, I should get back the identity operator. So if that is a inverse matrix exists, that means if I multiply with that particular matrix, I should get back the identity, right? So this is the left inverse formula for the full column rank matrix. And now let me move to the part called the right inverse formula. Okay, so if it is allowed to me, like I can take 5 minutes more class. If is it fine? Like then I can take maybe 1-2 questions from the audience. Like
Yes, sir, you can continue, sir.
okay, thanks. So just to cover this stuff. Yeah, right inverse formula. So now let's take a full row rank matrix. Full row rank matrix. In this particular case, rank is R and rank R equals to M, and possibly there is less row and more column. That is the situation, right? So, and in this particular case, my left null space, basically null space of A transpose equals to the only zero vector. So in this particular case, if you see the figure here, so I am only left with this part, and this does not exist. Only the zero vector. This only means the zero vector. This is the situation. In this particular case, I have independent rows. So I highly recommend to please at least watch the lectures by Professor Gilbert Strang, first 10 lectures, and you will appreciate why row space and column space are so important in algebra. Because that is the best lecture series, so I am not covering any part of that. Based on that, I am covering these things. Okay, application part. Okay. Now, how many free variables we have? So we have n minus m free variables. Now, if there are this many free variables, that means I can choose any m, any n for the solution design, right? So that means there are infinitely many solution. Infinitely many solution exist. Many solution exist for this kind of equation. Earlier, here in this particular two-sided case, only any so only there is a single solution. Single solution. There is two solution, either the correct solution or the one solution or the zero solution. Okay, here we have infinitely many solution. Infinitely many solution, and in this particular case, let's design the solution. So I have a and I have to reach I. What shall I multiply a in the right side so that I get I? This is my objective, right? So that means I have to find some a times a inverse right. That should give the identity, right? Now for this type of equation, what we typically do, we'll do the A times A transpose. Now A is M cross N. A transpose is basically your N cross M. Then A transpose will be my M cross M equation, because I have M number of independent rows and my solution should be designed using that, because that is the rank of the system. So what I'll do, I have created a square matrix out of this. So square matrix, okay. And suppose I do inverse of that square matrix, right? But what additional term I have taken? I have taken additional term of A transpose, right? So I have removed the additional terms. I can pre-multiply with A transpose, right? So basically A transpose will roughly will be out, right? So I will be left with A inverse. Actually, that should not be possible. It's a rectangular matrix, but just for understanding. So this is A transpose A into A transpose this whole inverse. So this particular thing is known as A inverse right. Right. So roughly what is happening? Roughly A transpose inverse, A inverse. So this part is identity. So only I left with A inverse, right? That is what I want to compute, right? So that means A times A transpose A, A transpose whole inverse. That is identity, right? So it is justified, right? So that's why this is called the right inverse matrix. So many books in least square formulation, only A transpose A based formula is given, but we need to remember as engineers whether more equation is there or less equation is there, more unknown is there or more less unknown is there, depending on we have to design the solution. Okay, so it's just not like running a single line code and it will give you the answer. Okay, now that is a term called the projector. This is important. Okay, so in often many cases, what happens is something like this. So this is your Ax equals to B equation, right? And this A is not pure A. This A is impure. That means noise is added here somewhere. Okay. Now to find the solution, what we do, we project on the, suppose this is my column space, and this is my null space. So if you project this particular vector with some projector, I should get back the exact solution. And if I project it to on the null space, this will be left with error. And this will be the solution. So what shall I multiply with this such that I get this solution? So now for example, A transpose A whole inverse for the rectangular matrix times A transpose, right? This is my left inversion technique, right? And I pre-multiply with A. So this is basically a projector PC. It is called it does the projection onto the column space. onto the column space. Okay. And similarly with the right inversion, A transpose whole inverse A. Okay. So this is called the PR, or the it is another projector which basically does the projection onto the row space. So accordingly, you can get X hat or the E hat error part. Okay. So basically, yeah. So please share the link to lecture series. Yeah, yeah. So it's YouTube. You can, okay. Somebody already has given, and you can YouTube. You can just simply write linear algebra by Gilbert Strang. So whole series is there. So yeah. So I mean, those are the prerequisite for this thing. Okay. And many of the things are already there, so you can appreciate. Okay, I shouldn't. Okay, I should find at least one more three slides. Just a few seconds. Okay, and the general case. What is happening? So the general case is that you have some X in the row space. This is always in the row space, right? And my solution X, that is always in the column space. And I have to design a projector that suppose what was my equation? My equation was Ax equals to B, right? So how do I find a solution to this equation? So what I actually get from the observation in the experiment is B. This is my observation vector, right? And I have some knowledge about the system A. X I have to compute. I don't know. This is my system, right? So now this is my observation vector. So this technique is telling that you should be able to project this B, P times the P is a projector on B, and this should project to the column space of this basically geometry, right? And which should give you the solution exact, right? And if you, because these are orthogonal, column space and null space are orthogonal, right? So if you do identity minus P times B, you should get error vector. This is my B vector. So basically this is what, this is my solution will be, X hat will be A times A times A transpose A whole inverse A transpose B vector. So this will be your ultimate solution. Okay. Irrespective of whatever your A is, but A is full column rank. A is full column rank. So this is your solution. Now later we'll see that A has several decomposition. A can be written as QR, where Q is an orthogonal matrix, R is an upper triangular matrix. A can be LU decomposition, U triangular upper triangular matrix. A can be decomposed as Cholesky decomposition, LL transpose. A can be decomposed as U lambda U star eigenvalue decomposition with certain condition on A. A can be for any generic A, you can always write U sigma V star, okay, as a singular value decomposition. And for all these various forms of A, you can better design some X hat. Okay. So that particular better design is called via a method called least square method. Least square method I'll cover tomorrow. So I am I today I'm so sorry I could not give some examples, but in my notes all the examples are there. I'll be sharing today itself, so it should reach to you. Thanks a lot. If you have any question, I can quickly take a few. And let me know the difficulty level so that I can tomorrow cover. Uh, Whether this level of linear algebra knowledge will be required for quantum algorithms, definitely all quantum states are vectors, all quantum gates are matrices. So without metrics and vectors understanding, it's not possible to appreciate quantum computing. I mean, to my understanding. Will be also covered. Yeah, tomorrow the entire day will be on diagonalization techniques, matrix factorization and diagonalization. 3 hours I'll be covering, and I'll try at least last 30 minutes, 40 minutes to show on the Python some real-time applications. Okay, some real matrices, and because it's a lab course, so some lab I will introduce. I hope I will cover that. Yeah, I think in the NQM recording, I think at least I took 15 lectures on linear algebra. Here today is very short time. I'm trying to cover some of the important stuff. But yeah. Um, any other question?
Sir, am I audible?
Yeah, please.
I think there are no more questions from the
Yeah,
participant side.
sure.
So thank you, sir, for taking this very informative session. I think the participants are beginning to appreciate that you need a lot of background knowledge also about maths. In the previous speaker, he taught us some differential equations, and now you are taking us into linear algebra. So good background knowledge is required for understanding of